Yes.
So we'll go to the other example next. You want to
We'll
break?
take a break.
Sure.
Coffee.
Sure.
So we can take about 10 minutes.
Absolutely.
Also have a class at this.
Sure. So we'll take a 10-minute break and assemble back at roughly 11:45. So we are going to look at deflection now. I already told you the three deflections: gross deflection, crack deflection, effective deflection, depending upon your I values, I crack, I effective. Let's look at some of the deflection related issues. Here we are talking about a beam 12-inch by 24-inch depth with a 2-inch cover, 4 of number 8 bars, that's about 0.79 inch square, and the span is about 25 feet. Consider long-term deflection at 3 months and 5 months. What is that?
5 years.
5 years. But what is that? That is the creep deflection. That's the key.
Long term.
Long term. Typically, after 5 years, they say creep deflection is pretty much constant. It does not increase. So it is an inverse curve, it goes up. About 60% of total creep deflection takes place within about 6 years. 80% takes place within 1 year. About. After, of course, there is going to be creep after 5 years, but maybe 1 or 2%, but it's negligible. That is the word. You will see some of that actually in the code. I don't know, that is the subsequent slides that I did not show is where I have the creep deflections as suggested by the code. I'm not sure I can quickly find those values or not. Yes, I did. Okay, we will look at that. I'll reiterate that. That is slide number 152. Okay, now mine. Okay, yeah, 152. If you look at it, time-dependent values for deflection. So what you're going to do is find you can see the coefficient is equal to 1 for 3 months, 1.2 for 6 months, 2.0 for 60 months. So they are saying, as you were asking me a minute ago, they are saying that after 5 years, it is pretty much same. So that's what we are going to try to find. This is the psi value is what's going to be modified, So I'll go over that later, but please look at it. So you have 3 stages. This is the instantaneous deflection due to the loading. And if the load remains constant, of course the load is a sustained load, not a live load coming in and getting out, a sustained load, then if it is a sustained load, it's going to go up. When you remove the load, the recovery will never ever be back to 0. When you remove the load, yes, there is some recovery, but that is less than the creep deflection, which is from here to there. So these are some of the issues keep in mind. So let me repeat myself. Immediate strain means what? Elastic deformation, MC over I, where M is the due to dead load, let's say, not due to live load. So that creep rate, creep deflection magnitude, they vary depending upon the percentage of the dead load in relation to its failure load. So higher the dead load, higher the rate of creep, of course higher the magnitude, we know that, but it also increases at a faster rate. So there are the two parameters there. One is the magnitude of the sustained load, and this is a function also of the time factor. I don't know how many of you are aware modulus E value is a time dependent function.
Yes, sir.
So if I have applied the load suddenly, I have a modulus higher than the static one. If I applied load gradually, I have a modulus that is lower than that. There is something in between. Therefore, how we are going to come up with a generalized theory that would account for the time-dependent modulus, that is a very fascinating topic. We have ideas, but we never came up with a unified theory for these different load rates. That's what we are working on, actually.
In pieces concrete also they will consider the creep coefficient when they are when they are considering the Young's modulus.
Right, which is, we call it as a very low load. If a bullet hits, that is a high speed. So there the modulus is higher. In creep, the modulus is lower than the static modulus. So you are always comparing higher or lower with the static value. Okay, that gives you an idea. Now we can go back to, yes, sir.
This recovery, what are we talking?
If you remove the load for whatever reason, some of the creep deflection will recover, but not all of it. Is that your question?
Is it same for both, like if you are taking like a slab or like pin beam type, wherever the horizontal geometry comes into picture, and when you see like columns, both will be like same or they will be changes?
That's what I just said, meaning depending upon the induced stress level, the rate of creep changes. Okay, let me quantify that. For example, my failure stress is 100 units, say. If I put 10 units of sustained stress, it's going to have creep. If I put 25 units, it still will have creep. But at a 10 unit level, the rate of creep is slower and it will reach certain value, whereas at 25 per unit level, the rate of creep is higher. It will go to a different kind of a value. That's what I'm saying. But after 5 years, it is leveled off. Creep tests are done for 15, 20 years, really. You have to keep monitoring, see what happens, how it does for different stress level conditions. So for a percentage of bending stress, for example. So with that, we'll go back to problem number 5. Slide number 200 something. 220. One more. There we go. Missed it. 214. Yeah, there. So now did you get it? Deflection corresponding to the creep issue. That's what we're going to be discussing. So along those lines, I did not talk about the deflection limit state. We have, these are the deflection limit states. There are 4 different values that depends upon which one do you use, the code, and where you use, the code clearly identifies. So, from my recollection, L/180 is the deflection limit state for cases of the roofs that do not have major failure concerns. The lower value, one L/480, roofs with a major concern. Okay. Deflection limit state in the US, we primarily state it's a function of human response, meaning as you keep walking, for example, then the floors vibrate. You don't want that. You feel odd when that happens. You know, that is a human response problem. In the olden days, most of you don't know, we still use wooden floors. You all don't use any wooden floors. If you go to villages, you still find wooden floors. They have a fairly high vibrational issue. That's why we have a deflection limit. Actually, that is a misnomer. Talking about the deflection as a function of span is a kind of a misnomer. It should be really related to the curvature. What is that? That's essentially the slope equation. L/delta is what we are saying is 180 or 480. 480? Yeah. See, that's L/delta. What is L/delta? It's a slope issue. That is not right, because I can have a tremendous curvature and have a failure, but still meet the L/delta as 480. You see what I say? Never mind, I don't want to get there. But another application where deflection limit state becomes critical is in the hospitals, where you have these MRIs, when if it is vibrates too much, gets off focus. So you want to have that. So primarily it's a human response issue or a sensitivity issue for medical instrument. That's where we have. So again, we will go through the same. So here, the important message I want to provide you with is the deflection limit based on creep, based on sustained load. The code is saying this is the key, that is the key step. Unlike your ultimate load combination that I gave you earlier for strength limit state, now I'm talking about this serviceability limit state. Here, you cannot avoid dead load. That's always going to be there. What they are saying is, to find the deflection, you are going to use 20% of the moment corresponding to the live load. That is the message I want to give you from this slide. Okay, so here you have the dead load there. WL square over 8 is a very simple case, and you have a live load there, and then the 20% of the live load moment is what we are talking about as a sustained value. So they are accounting for, if you remember that slide 155 or whatever I showed you, he was asking me a question about the recovery. So we are saying there is a residual deformation. There is a residual deformation coming from the live loads. In other words, there is no, just because the live load is gone, there is no full recovery. Of the regular modulus to account for creep. You remember that? In that range. Some people use 40%, some people use 33%, right? 1/3, roughly. That is the creep deflection. So you are going to compute total deflection, including the creep, by reducing the modulus to 1/3. That's a good bit. I mean, that's an easy way to do it. That component gets very difficult computationally when you deal with pre-stressed concrete beam design. I mean, that is an approximate number, but if you deal with a pre-stressed concrete design due to the pre-tensioned loads and what have you, you have to make a combination of live load, dead load, and the pre-stress loads. That is where they use the factor. That's what we use. I don't know what you use in India. 1/3 is our number for creep. Maybe while the
For pre-stressed too.
Huh?
For pre-stressed material elements too. It's 1/3.
No, we use 1/3 as the, I mean, if the modulus of concrete is 4.5 million, for static loads, for creep load, we say, no, it's only 1/3 of that, which is 1.5 million PSI.
Sir, the deflection, the significance of checking the deflection in 3 months and 5 years is that before 3 months it is just due to the sudden loading, not the creep comes into play.
Oh no, it does come. Remember, okay, let me state it in the following manner. I just said 98% of creep deflection takes place in 5 years. But I also said about 60, 70, 80% in the first year. In 3 months, approximately 40 to 50% of creep takes place. You follow me?
That's why 3 months is a significant.
You can see that from the equation there that the creep coefficient, that numbers 1, 1.2, 1.6 and 2.
Creep recovery.
So, no. Okay.
The value of epsilon.
That is, let me go back. Is it working now? See? Oops. Yeah, there. So if you see it, it is the creep deflection is about 0.6 or 60%. Yeah. Then it becomes twice that much in 60 months, and the rate of creep is not linear with respect to time. It is not. That is why we showed you the plot. This is the instantaneous due to dead load or whatever, but whereas after it hits the dead load, there is a gradual recovery. In this recovery process, gradual increase, I'm sorry. In the increase process, what we are saying is whatever the live load effect you have, we are only considering 20% of that over and above the dead load creep.
So it is said that until the load acts from the structure, creep doesn't start.
Creep doesn't start till you remove the shoring component. It only starts after you remove the support condition, the shored conditions.
In the initial portion, it is acting because of dead load.
Even that is zero. But initially, once you remove the shoring, that immediate is primarily due to dead load, but you could have some live load as well, meaning it doesn't have to be human beings as the live load. There may be other kinds of live loads, like people walking on it, you know. What we are saying is that live load for computational purposes is only 20% from creep deflection computation point of view. Okay, so we go back to page 215. So the message in this, all the others are same, WL square over 8 or whatever, all that is same. But what is not same is computation for moment corresponding to the sustained load. That is the difference. And this is the modular ratio. Then we move on. So here, I already told you the gross moment of inertia is 13,000, and look at the cracked moment of inertia is 2,200. That's where I said it's about, in this case it is 6.5 times, it could be of the order of about 10 times for a cracked moment of inertia. And then you see how we found the cracked moment of inertia? 1/3 BD cube, but that D is the effective depth, that's why it is KD cube. K is the factor that defines the solid portion of the section, and that's where you get the neutral axis. Then you have added on, what is this? AD square effect. What is the AD square effect of what? Of FRP. You see how they compute the number? And that turns out to be 2,200 compared to the gross value. That's about 6 to 7 times, you know. Oh yeah, it's right, given right there, 6.24. Now let's look at the cracked. Where is the M cracking coming from? That is, MC over I is equal to FC. What is that? 7.5 times square root of F prime C. That's the 10th rupture value, we call it. And from that rupture value, 7.5, you see all that, you can MC over I type stuff. 7.5 times square root of F prime C. And lambda is a multiplier for creep. We already told you. Lambda is 1.2 or 2.0, depending on the number of years of creep you are accounting for. So that is M cracking is F times I divided by C. That's exactly what that is. F, that is 7.5 times F prime C is the I divided by C. And lambda is the factor corresponding to, in this particular case we're taking lambda is 1. But now the question is, that is IG is all right, that's a general term, but now we have to worry about, is it IE or I cracking or IG, you know, that is the question. So as you can see, M cracking is 39.5, M dead load, live load without any factors, and that number is 0.7. And this is the empirical equation given by the code to establish the I sub effective value. This is the empirical relation. Therefore, I need this ratio to establish what that gamma factor is as per the code equation chapter 24. So I effective, you remember what I told you? I don't know you remember or not. This is approximately twice the cracking value, if you recall. So that's what we are talking about. So it is this IE is what we are going to use to establish deflection under service loads. So what is the difference between deflection under service load and deflection at failure? If I have, let's look at it from the standpoint of the physics. If I have a beam under bending, meaning some applied load, there is going to be a crack like this under service load. But on the other hand, if I'm going to take it to failure, that crack is going to go up to there, and then ultimately it will fail in local crushing of concrete. Now, we are not talking about totally cracked system, no. For service purposes, we are talking about I effective, meaning it cracked all right, as we discussed this morning before the break. How much did it crack? How much do you think it is cracking? And that is what is established empirically based on lab type testing and what have you. This equation, this is the critical equation, and that is tied with M crack is the section property, M sub A is the applied load based property. And when you talk about M sub A, that does not include your load factors. Ultimate values are different. They need to have a clarity in terms of the design. Ultimate strength design values are different from serviceability based design values. So, as I indicated to you, this is approximately twice that of I cracking. Now you understand the difference between a cracked section versus effective section? Okay. So this is why we say in steel reinforced beams is a tension failure in steel, but it's a primary tension failure, secondary failure you have. Ultimately it fails in local crushing. But we don't want things to go that far out of control. Okay, so now you can see immediate delta with k is equal to 1. That's a length factor in the delta using I sub E. That equation, empirical equation I showed you in the previous, is a very conservative number equation. And you can see the I sub E and then delta corresponding to dead load, live load, delta corresponding to live load only, and the difference is 0.37, and the delta corresponding to sustained load 0.305. So the delta from the unsustained load is 0.457 minus 0.305. So that is the delta from the unsustained load without multiplying with a creep coefficient. Now you have to multiply with a creep coefficient to establish the total deflection, including the creep, for the sustained load condition. There we go. Incremental part of delta, after placing non-structural elements, some of the long-term delta from all sustained loads and the immediate delta from additional live loads. Now for 3 months, you can see we have already computed these numbers in the, in the previous slide. These numbers in the previous slide, you remember 305 and all? The sustained load numbers. After 5 years, you can see how much the deflection has increased due to creep. Almost 50%. Little more than 50, but in that range. So the creep has a tremendous impact on limit states corresponding to the deflections. So that is my message. Compare the computed delta to deflection limit states. So these limit states that I'm showing you here, L over 180, L over 360, it is given under what condition they're applied. The definition is given right there. For flat roofs without non-structural elements, it is L over 180. For flat roofs without non-structural element likely to be damaged by large delta. Okay, so now you have to worry about the allowable values that are for different kind of scenarios. There are 2 others. You remember I gave you 4 of them: L over 180, L over 360, L over 240, and for L over 240, floor supporting non-structural element not likely to be damaged, floor supporting non-structural element likely to be damaged. So these are defined by the code. We have nothing to do with it. So you have to satisfy all these items. If they don't satisfy, obviously what do? You go back and increase the size of the section, or increase the amount of reinforcement, or the quality of your material, like concrete strength, you know, one of those variables. Huh? Okay. One is flat, you're talking about this, flat roof without, and the one is with. Sorry. No. There is an editorial error. Did I answer your question? No.
Which one is
I couldn't hear.
So which one is without non-structural elements and which one is with?
Okay, I'll throw the question at you. What is the common sense telling us? Okay. The first one is not likely to happen. Wherever you have less risk of failure, the limit state is lower. Wherever you have a higher risk of failure, the limit state is higher. That's what it is. Okay. So you can see the factor is going up by 50%. I don't know how many of you all design the floor systems for deflection limit states here in the country? You do? Yeah. We not only do this, we also have another limit state in terms of frequency. Now, the first fundamental frequency should be below 3 hertz, for example. That is tied to the human response. 2 to 3 hertz is tied. So either it should be below 3 hertz or above 6 hertz. Between 3 and 6 hertz,
Resonate.
things come close to resonance. They don't resonate, they come close to it. Okay. So we talked about limit state from the standpoint of deflection.
Yes.
Now we need to look at the same kind of a limit state from the standpoint of creep rupture stress check. So it's a rectangular beam, 12 inch by 18 with 3 inch cover, 4 number 8 bars, carries the load. These are just some numbers really illustrating the point of the principle more than anything else. And assume that 20% of live load is the sustained value. So again, the drill is same. Concrete modulus, we said that 100 times. The rho values, we know how to determine. Area divided by the cross-sectional B times D. D is the effective value. 3 inches is the cover. So again, we want to talk about sustained moment. There's the dead load is always 100% sustained. 20% is the live load sustained.
Sir, if nothing is given in the statement, then we have to assume only 20% of the live load is being sustained.
Correct. Correct. That is by default. You may have a much higher sustained load due to utilities, for example. You see? So that you have to check it. If nothing is given, you assume 20%. So we find the eye cracking as we did before. The first term is a 1/3 B kd cube. The second is the AD square effect. Eye cracked value is 861. So the allowable stress is 6.55 less than 0.2 FFY, 14.4, therefore that check is good. So creep rupture, find U stirrup size and spacing for 20-foot span simply supported beam. Here the B and D values with a 3-inch cover, 12 inch by 24 inch, the D effective is 21 inches.
We are changing the power from DC to
Oh.
right. So
Oh, that's fine. So while we are at it, all I want to say is we talked about the bending cracks going from bottom up, and at some point the concrete will crush, and the effective depth of the neutral axis for steel is about 15, 16, 17%. For FRP is about 8%. Whereas the shear crack, I don't think this will work, the shear crack is going to be something like that. And this is where I want to repeat myself. The L/D value. So L/D value is say around 20, 24, definitely less than 36, 38. This is bending failure. Whereas for a shear failure, L/D is less than or equal to 12, less than or equal to 6. So this is the shear failure. Okay. So now we are going to another example where we will have a creep rupture stress check. Find the U stirrup size and spacing for 20-foot span simply supported beam. So we gave you the loads and the member size. Why did I say L over D should be less than 12? It's a shear failure.
Yes, sir.
That's the reason I reminded you. And the CE value can be 0.8 or 0.85 depending on the code. And that support, 20-foot span, is, I don't know how much you all do here in terms of shear critical section. Do you all use it at the support, or do you use the critical section at a distance D from the support? Yeah, I want to repeat this. Typically, the critical shear section is at a distance D effective depth from the support. Only, wait a minute, that's partially correct, partially incorrect statement. That is, if you have any concentrated loads, any other special loads, or the loads are placed at the bottom of the beam as opposed to the top of the beam, then you should not take the critical section should be at the support, not at a distance D from the support. Do you get it?
In Indian code, they'll say that when your support reaction creates the compression on the beam, then that is at a distance of D from the face of the support.
That's right.
If your support reaction creates the tension, then it is at the face of the support.
Yeah, that is what I mean. If I have a beam, what did we say just now? Critical section is not here. We are saying critical section is there, right? But that is at a distance D, where D is the effective value, correct? But what we are saying is, that's correct partially. If on the other hand, if my load is not here, if the load is say here, for example, I'm just using that as an example, then you have to take the value 0. That is, okay, all right. That said, let's move on. So, that's, oops. So that's what we are talking about. Okay, 5 kips per foot. So the V at a distance D, we have proportionately reduced that effect. That square root should come right here. It did not. It's a typographical error. Phi factor is, as you know, even today we don't fully understand how the shear functions on a cross section. Therefore, you always have a higher, uncertainty, therefore lower phi factor. And this equation is given by the code. The K value is established based on that equation. I'm glad we talked about it first thing in the morning today. The phi factor is 0.75. Correct. So the square root value is properly placed here, unlike on the previous one. So the phi V sub C is so much. I don't know whether the same thing requirement in the ACI code for in India or not, but we say you don't need any stirrups if the V is less than that. In other words, in this case, you do need stirrups, but we say you do not need any stirrups if it is less than that. So, that V is missing here, VU minus VC. So if you have the value of shear higher than this, we have to modify the section. In this case, it is not, meaning 8 times square root of f prime c is our limit. And that's the upper bound. If it is the case, we have to modify. And the lower bound, it is 2 times square root of f prime c. We already checked that. That's what that is, 2 times square root of f prime c. So here we satisfied the upper bound in terms of stating that stirrups will do the job. That's what it means. If it exceeds that number, then the stirrups will not do the job. You have to increase the cross section or increase the property of the material. That's what it means. Again, we are assuming that the critical section is at certain distance at the support, and that is the ultimate load. Therefore, we have established the distance from the support beyond which the shear or the reinforcement is needed. So find the distance from support beyond which shear is not needed. So between 7.4 and 8.7 feet from the support, you don't need it. So we are trying to provide the stirrups in that zone. So minimum shear is needed between 7.4 and 8.7 from the support. Shear GFRP not needed beyond that. Now you know how to compute that number. That's the magic number. You have the same.
Yes.
Okay. Design tensile stress in terms of shear for the stirrup. You remember the equation we provided you with? And for the stirrup, and the value is 32 kips. The tensile strength corresponding to that, if you recall, is 24. So we are safe. That is the check for stirrups under tension. This is the stirrup spacing equation. As I told you, you cannot get an equation simpler than that. That is the required shear, that is the shear resisted by concrete, and this would give you the area requirement for the stirrups. From there, I derived this equation yesterday, if you recall. Check maximum permissible shear is, this is what needs to be checked, whichever is smaller. And the maximum spacing based on the minimum shear. This is a check, that is the max spacing. And if your stirrup spacing based on this comes out to be larger, this would control the section. But typically, this equation controls the shear reinforcement. That's very typical. And I already informed you earlier, we are not going to use a strut and a tie model in the code. Does not permit it because you don't have the what we call the yield kind of an effect in FRP. So the section is 5.4 inches. We are using a 5-inch stirrup spacing. But we already did the check, and that was the idea of this example. Okay. All right. Any questions? Maybe the audience, some of the. Any questions from the audience?
the steel reinforcement and all. So because it yields, then we consider the redistribution of moments, especially in indeterminate beams or indeterminate slabs and all. But the similar redistribution.
No. Good question. Very good question. I don't know how many of you appreciate the redistribution concept. In steel, you do have a redistribution. Here, we do not allow any redistribution. Because being a compression mode failure, once it hits the limit state, it's going to fail. Unlike in steel, it's a tension mode failure where it hits the yield value, I still have a plateau, then I still have strain hardening zone. We do not have that luxury in this. Therefore, the code clearly states you cannot use redistribution concept with FRP. That's a very good question. There's a lot of debate on that, but they finally concluded no redistribution. And the court said that in many different locations, not just one location, 3-4 locations it did talk about. So they're alerting the designers not to get into that. This morning I was talking about connector details a little bit, not a whole lot, but try to form the reinforcement in a manner that would attempt to establish a hinge type location beyond, over and above cracking. So what does that mean? That means if I have the redistribution thing he is referring to is as follows. If I have a column and a footer, how do you form a hinge? So you provide a reinforcement from top down, bring it to the bottom, left, from right to left, likewise from left to right. And you have stirrups there, and that is your zone where hinge would form. So it's very important in FRP because of compression type failure, because of lack of ductility. It's good to have wherever possible. I wouldn't even do much research work. Maybe it's okay to have a baseline value, but I would always focus my research in terms of systems that have a hinge formation. In other words, I will not bother about testing a system going this way, this one going that way. No. So this kind of a thing is out. In any in any non-ductile system, you are better off using wherever two things. One is the formation of a hinge, the other is confinement of the material. You figure out how to confine in theory, I don't know how much you appreciate, if I have a bottle, this is in theory, if I do a compression test, this is going to fail in certain mode. If I fill this with sand and then wrap it, in theory, when I do the compression test, the load is infinity, in theory. Of course, that doesn't happen. So it will increase by 7, 8, 10 times more. That is the definition of confinement. So if you can confine a concrete, even a little bit, like why do you think the spiral reinforcement by itself, or even better yet, you confine the columns with FRP composite fabrics? I don't know how prevalently FRP fabrics are available, how extensively you are rehabilitating with FRP in the country, I don't know. But now in the US, we are really doing a lot of rehab with FRP wraps. So my message is confinement through wrapping or confinement through this type of a hinge formation between the reinforcements and the stirrups will give you this kind of confinement easily will increase at least the ultimate load by a factor of 2. Ultimate load, I said. Not necessarily the initial crack load, but on the other hand, if you wrap it externally, even the initial crack load will go up 2 to 3 times. Of course, that all depends on how many wraps you have, what is the stiffness of the wrap versus the core material, blah, blah. All those are there, we know that. Nevertheless, the simplest message is confinement in different forms. Not only it gives you increase in strength, maybe much, maybe not much, but certainly, no matter what, it will give you a tremendous increase in ductility. So all our systems need to be viewed upon more from the ductility point of view to avoid catastrophic failure. Of course, we want functionality, we know that. That is where the serviceability comes into picture. For the failure, preventing the catastrophic failure, that is where your confinement and the ductility come into picture. You have a question there?
No questions.
Okay, maybe you might ask.
On that part, that discrete fiber, what you told us.
Say it again?
Discrete fiber. That,
Discrete fibers.
That may also help on that.
Of course. Oh, absolutely, absolutely.
Pseudo ductility will be.
Right, right. If the concretes are commonly used, let's say, with these chopped fibers, obviously it's going to increase the ductility and this. Even sometimes the failure mode changes, then it will no longer be pseudo value, it will become a common value, you know. That's why I don't understand, I said that 3 times today, why it didn't take off with fiber concrete. It's not all, you see, when they are delivering this with these concrete mix machines with the plastic fibers like polypropylene or whatever, synthetic fibers, I don't know why they're shying away from it.
Actually, workmanship plays a major role in preparing FRC, fiber reinforced concrete. Because the handling workability is very, very difficult, especially the larger percentage.
Even with the super plasticizers?
We have, but how we are controlling in the site is major.
Yeah. Anyway. Yeah, okay. Now, so anything else?
Yes, sir. In beams, generally after support, so generally we provide 35 times LD for the development length of whatever. So 35 times diameter or 37 times diameter. So in FRP, since we are not able to bend it in the site, so what precautions we have to take?
This is a common question we are facing with. Therefore, they would bend in the factory and bring it. That's the common thing we are finding. Therefore, obviously, it is not as continuous as it is in the steel, but that's why our, as you can see, if I remember right, the overlap lengths are 40 or 46 times the bar diameter as opposed to 36 or 32 times the bar diameter in steel. So we have a slightly increase, about 25% increase in the overlap length due to FRP over the steel reinforcement. I really fail to understand why even they increased it, because FRP has a slightly better bond. Of course, it depends on the type of a surface characteristic. At least the sand-coated one, slightly better bond than ribbed ones, you see.
Actually, in India, we get very lesser bond between concrete and FRP than steel.
That is, I know, I heard that, but maybe again that's a quality control issue, and the curing issue, how you manufacture it. This is a two-stage curing. So if you wait too long and then roll it in the sand bed, obviously it won't stick as hard, and also it could be a resin-based issue too. You see, so again, I don't know enough here, but I can tell you from the US side, as you have seen some of the numbers I gave you, it depends, of course, on the quality, but by and large, again, nobody, I do not see people even in US exclusively using sand coated. They are using either ribbed or a combined effect of sand plus ribbed. I haven't seen, actually I put in the McKinley wheel bridge both, the sand coated and ribbed, both I did. That's being a fairly big size bridge, I had the luxury of putting both. I put half of this and half of the other. I actually put two different manufacturers' FRP rebars in there. Okay, is there any question there? Okay, so before I go into the development type issue, lunch break? Okay.
10 minutes.
Another 10 minutes.
Okay.
Any questions from audience?
One question based on that. Sorry,
Sure.
Actually, as you suggest a suggestion for overcoming the wear and tear and the strength problem, also to wrapping the columns and to enhance the strength of the existing structure due to the age and or wear and tear. So, that is with the strength, the internal stresses also they induced by certain loads. They had the load carrying capacity of the structure. It enhances.
Oh yeah.
Wrapping.
Okay. How should I answer that? Okay. Wrapping undoubtedly increases not only the strength, of course strength increases much more, but also increases the stiffness. That is not because suddenly your concrete has somehow magically gone higher in strength. No, it is something because of the confinement. Now, that said, I said also the stiffness increase. That's not much because, okay, qualified. That's not much when you wrap with glass fabrics. You could get that pretty high when you wrap with carbon fabrics. Yeah, it depends on the carbon grade you are dealing with and so on. So, but yes, you can get about 10-15% increase in stiffness with glass, 30-40% with carbon. But whereas when the strength is concerned, don't waste time and money with carbon. You can, if you're strictly looking for increase in strength, glass wrap will do the job. Strength increase, not the stiffness increase. Even in the glass wrap, there is an increase in stiffness, but not much. I don't know whether I showed you, we have rehabilitated a bridge, a 42-foot high column that had a gaping hole all right across the length of the column, and then we did the rehab of that with carbon wrap. That is why that bridge is a skewed bridge, and it is in the slope, all kinds of things. Therefore, we went with carbon. Or else, for durability purposes, like big size columns, that bridge, that column is like a frame type column, not a mass column that bridge required that acts like a portal frame. So it is a bending issue. Most of the columns we deal with don't have that. In such a case, a glass strap will do the job.
So coming to the application, sir, can we use this one in 10 elements like shells and FRP usage?
Yes, the simple answer is yes. There was a temple built in DC area with FRP. One has to be very careful in terms of how you design, but I forgot the name. It's something close to a lotus temple or something like that. Nothing to do with your Delhi lotus, so don't get confused. There's something like that they called it, and it worked out well from a structural point of view. It did not work out well from a durability point of view because they did not understand 2-3 things. One is the creep, and the other is the UV degradation. They didn't administer adequate UV inhibitor. This is outskirts of Washington, D.C. They did that, and then I don't know what happened.
So coming to the creeps, a element is in one directional element or a two directional element, how the creep is going to be affected by the movement distribution in two directions?
If it is a one-dimensional element, you have a creep in one dimension. If it's a two-dimensional element, you have a
then
creep.
In that case, the shell structure will be more effective compared to that.
Again, from a stress distribution point of view, you need to be thinking how the forces or stresses are distributed, So that is, from deformation point of view, I think the deformation is a follow-up of the stress, So I'm not sure I am able to answer your question fully, but it's a two-dimensional problem. I'm trying to, or actually it may even be a three-dimensional problem.
Even in plane forces and shape.
Right. If you can convert the bending forces into axial forces, you're in business, you see. What is that? What did I mean by that? That is, the old arches are almost all are axial effect type thing compared to, so they essentially converted the bending into axial effect. So if you can convert the membrane effects, for example, that we deal with, are all in-plane forces, then if you can convert that into tensile forces, you have better luck with creep than compression forces. Yeah. That's why I'm hesitating to answer your question. I'm thinking while talking. At any rate, I don't want to give an answer, but it should work out if the forces are turned into in-plane forces. Yeah.
It's one of lecture we will elaborate.
Okay. Any question? Any questions?
No questions.
Okay.
So again, we will assemble at 2 o'clock.
So here we want to talk about development of bars in tension, compression control or a transition. You want to reduce that a little bit, the size? Yeah, good. So what we are looking at is zones AB and AC, where you are talking about the development length. The clear cover is 3/4 inch. This is the development length for number 8 bar embedded in one-way slab to develop full moment capacity. So you can see the bars. So the values. Okay. Again, the drill is same. F sub FU is 80 KSI or 85 KSI depending on 0.8 or 0.85. The effective depth is clear cover minus half the bar diameter, 14.75. And the rho F. Here, how do I find the area of the bars? So, as you can see, we are looking at a unit width or a unit, meaning 1 inch width or a 1 foot width. That's a very standard approach.
Yes.
You keep it very simple. So that is what that is. So you're talking about the bar area per foot length of the slab. So from there we found the rho F, and then compare that against the balanced value to understand whether that is high or low. And obviously rho F is twice that of rho balanced, therefore it is compression control.
More than 1.4.
Right. So you can see the tensile stress in the FRP based on that standard equation we're talking whole day today. That turns out to be that way below the rupture stress of the bar, which is 80 KSI. So the important message of this slide is find the stress in the bar which must be less, otherwise it's not a compression control.
Yes.
That is the point. If you got something higher than 80 KSI, something wrong with your computation, That's what we did. So again, please note, these equations that are given to you here are empirical in nature. And that is the code equation. I forgot to mention the code equation number, but that is the code equation. And I defined what is C, which is the minimum of the cover, center spacing divided by 2, or this should be less than 3.5 dB. All these, you might be wondering where we got it. All these came from testing procedures. That's what I keep saying, empirical relationships. So from that, the C value is 1.25 inches. The bar diameter is what, number 8 bar. So we can substitute it in there. And based on that, the required LD is 63 inches. So somebody was asking me, Indian code has 36 or 32 times bar diameter, and you can see this is much higher than that. I need to qualify. What this 36 they're talking about is with respect to steel, and with respect to composite, it's almost 60 times. That does make sense, implying that when we run the tension test, we are finding you get a better value with a larger gauge length as opposed to shorter gauge length in tension. So that falls in line, and this equation came about in the sense of empirical experimental work. Most of this is done in Canada. Most of that work, yeah, they are doing pretty good job. Okay. So the dB is 1 inch diameter bar. That's compression control. In the tension control, find L sub D for the inner two number 8 bars at a column face. Obviously, near the column, it's a tension at the top. That's what we mean. So 2 number 8 bars are continuous along the length of the full beam. If you remember, you have seen that about 6 slides before. And what is given is 4,000 psi concrete, 80,000 psi, before correction, 6,000 ksi, modulus, that is the depth, effective, beam size is 12 inch by 30 inch with 2.5 inch cover, and the side cover is 1 point, that's given. So it's the same thing. We have a total value of area, 4 times 0.79. There are the 4 bars there in that top of the column interface, and that is 0.0096 rho F, and rho F or rho B is very close to 1, but still slightly less than 1.97. Therefore, we call this a tension control. Yeah. And again, this is the formula. We substituted all the values. So we got a much higher, previously it was about 63 inches, now it is about 79, 80 inches. So again, that falls in line with what you expect as a common sense type thing. The numbers you may not know, but it better be higher from a tension control over a compression. So this is a two-way action shear strength by concrete at interior column support. So what you're looking at is an 18 inch by 18 inch column with an effective shear transfer area is 18 plus D. That's a very standard, everybody accepts it based on your 45-degree angle type. That's where it comes from actually. So again, these are just some numbers. We are keeping it consistent. That's about it. The plate thickness effective is 6 inches. Probably the total depth is 7.5 inches. The punching shear without any shear reinforcement. As you know, just reminding you, this is 0.75, and the shear strength of the concrete is, there are two formulae they are using. Here you can see this is one of the two given by the code, and the K factor based on that quadratic equation. We have already defined, if you recall, the rho F value, and NF is close to 1, and you substitute various values there, and what you get is 0.18. You keep talking about KD value in the range of 15-16%. So sometime you can run the computations with these standardized numbers like K of 0.18 or 0.16, that type of thing. And if you go back, the B0 is the perimeter of the shear area. That area, that is the shear perimeter, and that's what we are showing there. B0 is 4 times 18 plus 6. So that 4 comes from the perimeter. The punching shear is given. The equation for the punching shear was given in the earlier slide right there. And that is the equation we use. So the concrete capacity to resist punching shear in this case is 49 kips based on that empirical equation. So that's a very simplistic approach.